Now that we've mastered the mole, we're moving on. We're moving up in the world. We're going to look at the concept of percent composition. Percent composition is exactly what you would expect. It's like a percentage, where it's the mass of a part divided by the mass of a whole. In chemistry, we usually think of it like this. I'll have a compound, and I want to know what percent of the mass in that compound is coming from a particular element. So I divide the mass of that element by the mass of the compound, multiply by 100 to get a percent. Game over. Just like any other typical percentage, part divided by the whole. We can use this in a couple ways. There's a law of definite proportions that says if I have a particular compound, maybe in this case carbon dioxide, well, any sample of carbon dioxide has to have a definite proportion of elements. It means like a constant proportion. So on a small scale, I could read this as one carbon atom and two oxygen atoms. There's no other substance that has all the same properties of carbon dioxide as when carbon and oxygen bond in a 1:2 ratio. One atom of carbon for every two atoms of oxygen. The law of definite proportion just means that if you're going to call something carbon dioxide and it's going to have all the properties of carbon dioxide, then it has to have the same structure, the same proportions of elements as carbon dioxide. That on a larger scale, I can't really measure an individual atom. So instead of atoms, we might read 1 mole of carbon for every 2 moles of oxygen. Whoa, oxygen. And moles is a unit that represents a number of particles. And so if a mole is always the same number of particles, 6.02 times 10 to the 23rd, I'm still keeping the same ratio. I'm supposed to have twice as many oxygen atoms. Whether I'm thinking small scale or now large scale, if I had 1 mole of carbon and 2 moles of oxygen, I still have double the amount of oxygen atoms. Now eventually when I want to go to the lab and do this, I can't really measure moles directly. I want to measure grams. So maybe I'd say, look up the molar mass. Approximately 12 grams of carbon. And if I went 2 moles of oxygen, oxygen's molar mass is about 16. So if I had 32 grams of oxygen, that would be the proper mole ratio. 1 mole of carbon is about 12 grams. 2 moles of oxygen would be 32 grams. And then I'm still keeping this consistent ratio. That's kind of the law of definite proportion, that no matter how we look at carbon dioxide, it'll always have a definite composition or a definite proportion of elements. Whether we measure individual atoms or maybe on a larger scale, we use moles. And from moles, we can get molar mass or grams. And so again, the concept here makes sense, I think, that we're looking at a part divided by a whole. So in question 20, when they want you to come up with an investigation to determine the percent by mass of cashews and almonds in a jar of mixed nuts, were you thinking something like percent mass of cashews would just be the individual mass of all the cashews divided by the mass of the sample, the jar of nuts, the jar of mixed nuts. Maybe I'll say by the mass of all nuts times 100. So I'd have to pick out all the cashews, take their mass, then I'd have to add them back in and find the mass of all the nuts, and then divide. And we could do the exact same thing for the almonds, where we would just pull out all the almonds, find their mass, put them back in, and find the mass of all the nuts together. Divide the part by the whole, multiply by 100, you've got your percentage. Now, realistically, in chemistry, we're probably not going to be measuring mixed nuts. Instead, we look at percent composition with compounds. And so here's a great example of how this has a little more of a chemistry spin to it. When a 13.6 gram sample of a compound containing only magnesium and oxygen is decomposed, that just means when the original magnesium oxide compound is broken apart into its individual elements, magnesium and oxygen, 5.4 grams of oxygen are obtained. What is the percent composition of this compound? Awesome. Well, here's my data. I know the mass of the compound. They gave me the mass of the oxygen. Now, even though they didn't directly tell me how much magnesium was present, I can figure it out. If I know the overall mass of the sample, and I know that it only contains magnesium and oxygen, if I take the sample and subtract the oxygen, then the rest of the compound is magnesium. This massive compound, that's like magnesium oxide, because magnesium is a +2 and oxygen is a -2. Oh, that makes sense, because then in the end, the mass of magnesium plus oxygen should equal that 13.6 gram sample. Okay, so there's a couple ways to attack this, but at some point, we're looking for this. Okay? We want to do a percentage as mass of an element divided by mass of the compound. So once we had the mass of each individual element, we could take that mass of magnesium divided by the mass of the compound. Mass of the oxygen divided by mass of the compound. In the end, you know you did it right if you add up your percentages and they equal 100. 100% of the mass should be coming from the magnesium plus the oxygen. Now, realistically, if you were just asked, what is the percent composition of all elements in this compound? What if you just did the magnesium, for example? I wouldn't call this lazy, I'd call it resourceful. What if I just did the percent magnesium? Could I then find the percent oxygen? As long as I'm pretty confident that I did the magnesium right, then you could just take 100% and subtract the 60.3. Oh, what do you know? Magnesium. And the difference should be perfect, the 39.7% oxygen. So obviously you can set each of them up as mass of the element divided by mass of the compound. In the end, you can double check your work because they obviously should add to 100. Or you could just do 1 and then take that percent, subtract it from 100 to get the percent composition of the other element. Oh my gosh, this is almost sounding kind of fun, right? It just makes sense. So let's try one. When a 14.2 gram sample of magnesium 2 oxide is decomposed into its elements by heating, 13.2 grams of magnesium is obtained. What is the percent composition of this compound? Fantastic. Okay, so I've got 14.2 grams of magnesium oxide, and I heat it. It breaks down into its elements. Now, realistically, if you were doing this in the lab, the oxygen gas is just going to go off into the air. It's a gas. But what you'd be left with in your container would be the liquid mercury, the metallic liquid mercury metal. So this is pretty typical data in that I don't know how much oxygen was in the compound because that's gone, that's off into the air. But I do know the amount of magnesium left behind. Mercury left behind. Now we could figure out the oxygen if I take 14.2 grams. This is mercury 2 oxide. Oh, well, that's kind of nice. It's neutral. If I take the mass of the compound and subtract the mass of the mercury, the remaining mass should be the oxygen. 2 minus 13.2 gives me a big fat 1 gram of oxygen. Well, now I could do the percent composition. Let's say I do percent mercury. That would be mass of the mercury divided by mass of the compound. 14.2 grams of mercury oxide times 100 to give me a percent. All right, so 13.2 divided by 14.2 times 100. And as far as figures goes, my calculator is full of digits. If the original numbers gave us 3 digits each, let's just round this percent to 3 digits. So maybe I'll say 92 point, oh brother, it's like 92.95. I'm going to say 93. I'll say 93.0% mercury. Now I would do the exact same thing with the oxygen. Percent oxygen would be the 1 gram of oxygen divided by the same total mass of the mercury oxide times 100. Now I'm hoping my answer is 7, right? 1 divided by 14.2. Yeah, I mean, if I leave this as like maybe 2 or 3 digits, I mean, it's like 7.04, which obviously I rounded the first one a little bit. Let's say 7.0% oxygen, because I know I did it right if these two add up to 100%. Now again, if you felt really confident with the magnesium, then right away you could say, okay, I know that it's now 93% magnesium, so the rest of it must be oxygen. The other 7% must be oxygen. So maybe you could get away with only doing one calculation and then just subtracting from 100 to get the percent composition of the other element.